Hello everyone, I'm Paul and today we're solving problem 2872, maximum number of k divisible components. This is hard, but once you get the main idea, it becomes easier. So let's start. We are given an undirected tree. So let's say that we are given this. Here we have 5 nodes, we have n-1 edges, and we have an array values with values for every node. For example, values at 0 is 1. This means that the value for node 0 is 1. Values at 1 is 8, values at 2 is 1, and so on. Now we are also given an integer k, and we have a valid split if the sum of the nodes in this component is divisible by k. This is in the constraints. We know that the sum of values is divisible by k. So if we take 8 plus 1 plus 4 plus 4 plus 1, we get 18. And this modulo k, meaning 6, is 0. This means that 18 is divisible by 6. So this is a valid split. The thing is that we need to return the maximum number of components in any valid split. And we can get different valid splits by removing one or more edges. For this example, we can remove this edge, and now this component has a sum of 12 modulo 6. The result is 0, so this is valid, and if we take this component, the sum here is 6, modulo 6 is also 0. So this is a valid split. Now we have two components here, and given that this is the maximum number of components in any valid split, we just return 2. Maybe you are thinking about starting from the root and taking the current value modulo k and checking if this is 0. In this case, this is 2, and given that we get 2, this means that 8 is not divisible by 6. So at this point, we should add another node. If we go right, we add this, we do 8 plus 4, 12, and 12 modulo 6 is 0. So now this is a valid component. If we add this node, here we have a valid component. Now, how do we know that we need to add this node? Because we could add this one instead, or we could even add these two nodes. So as you can see, if we start from the root, this can become messy quite quickly. Now, what if we start from the ellipse? Let's say that we start up here. The current value is 4, and this modulo k is 4. This means that 4 is not divisible by k, so we need to take a new node. And here we only have one possible edge, so the only node that we can take from here is this one. So if we add this now, the current sum is 12, modulo 6 is 0, so this is a valid component. And this is the main observation for this problem. If we start from the ellipse, every time we only have one way to go. If we are here, we can only go here. If we are here, we can only go here. And with this in mind, you can solve the problem with DFS or BFS. Here I will show you a BFS implementation that I think it's very interesting. How do we know if we are standing at some lib? Well, we know that for each of these, we only have one edge. So we can count the number of in degrees, which is the same as the number of incoming edges. And we know that the nodes with only one incoming edge are libs. And maybe you are familiar with something called topological sorting. This is something that we use with directed acyclic graphs to iterate nodes only after the corresponding dependencies for every node have been already visited. In this case, the graph is not directed, it's undirected, but we can do something very similar. We can build an adjacency list and an in-degree array. In case you know what an adjacency list is, it's just a map where each key corresponds to a node and each value corresponds to an array with the neighbors for the current node. So if we are standing at node 1, the neighbors here are 2 and 3. And in case you know what an in-degree array or map is, it's just an array or map where we have keys or indices corresponding to the current node. Let's say that we are standing here, and the value for this will be the number of incoming edges. Here we have 2 incoming edges, so the value here is 2. So this is the final adjacency list, and this is the in-degree map. How do we know where the leaves are? Well, we know that they need to have an in-degree of 1. So we know that this is a leaf, this is a leaf, this is a leaf, because these values are 1. And we are using this as the source for our BFS. Remember that in BFS we start from some source and we move to the corresponding neighbors. And only after we iterate every neighbor, then we move to the next neighbors. So here you can see how we move in circles level by level. Only after we iterate every node in the current level, we move to the next level, we repeat the same, and so on. So in this case, the source is built with these 3 nodes, 4, 0, and 3, these leaves. Only after we iterate every leaf, we move to the next level. So now we have a queue with the leaves, and here in queues we use first in, first out, so we start with this node, meaning we are standing here. And first we need to remove the in-degree for the current node, because here we have an undirected edge, and this is as if we had 2 edges, one from 2 to 4 and the other one from 4 to 2. First we need to remove the incoming edge to node 4. Meaning we go here, we subtract 1, and this is 0. And by doing this, we make sure that we don't visit this node ever again. So now we don't have this edge, we only have this one. Next, we are checking if the current value for modulo k is 0. And here the result is 4. This means that 4 is not divisible by 6. What this means is now we need to add the corresponding value for this node to our only next option, meaning node 2. So we take this and we add it here. 1 plus 4 is 5. Now we can remove this incoming edge from node 2, meaning we go here and subtract 1, this is now 2. And we still don't add this to the queue, because from here we have 2 options still. We need this value to be 1 in order to add this to the queue. So now we continue with the next node in the queue, meaning with the next leaf. So we are here. And now we do the same. We go to in-degree at the current node and we subtract 1. This is 0. So now we don't visit this node ever again. And now we are checking if the current value modulo k is 0. In this case it's 1, meaning this is not divisible by 6. So at this point we can add this value to our only next option, meaning this node, and 1 plus 5 is 6. And now we need to remove the corresponding in-degree from node 2. So we go here and this is now 1. And given that now we only have 1 in-degree here, we are ready to add this to the queue. So now here we have a 2. And this 2 is part of the new level. Remember how BFS works. We start from one source, in this case from 3 sources, and once we iterate every value in the source, we can move to the neighbors. So this 2 is part of this new level. The next node in the queue is the last leaf, meaning node 3. So we do the same. We go to in-degree at 3 and we subtract 1. Now we are checking if 4 modulo 6 is 0, and it's not, it's 4. So 4 is not divisible by 6, meaning we need to add this to our only next option. And we need to subtract 1 from in-degrees at 1. So here this is now 1. And given that we only have 1 incoming edge here, we are ready to add this to the queue. Now we iterate the next node in the queue, meaning 2. So we are standing here. We only have 1 in-degree, which is this in-degree from 1 to 2. We remove it and now this is 0. So we will never iterate 2 again. Now we are checking if the current value 6 modulo k is 0. And it is 0, so this is divisible by 6. At this point we can add 1 to the result. This means that this is a valid component, that's why here we have 1 in the result. And now we can remove this incoming edge from node 1. So we go here, this is now 0. And given that this is 0, we don't add this to the queue. We only add this if this is 1. We already have 1 in the queue. So now we can continue with the next node. So now we are here, we remove 1 incoming edge from node 1. So this is now -1. And now we're checking if 12 modulo k is 0. And it is 0, so this is divisible by k. At this point we can add 1 to the result, this is 2. And this means that this is another valid component. Remember that this 12 is composed of 8 and 4. And now we reach the end, we have already iterated every node, so we return 2. So as you can see, we are iterating nodes only after we iterate every corresponding dependency. That's why this is very similar to topological sort. And time complexity for these graph problems is big O of the amount of nodes plus edges, but here the amount of edges is the amount of nodes minus 1, so we can say that this is overall big O of n, and space complexity is the same because we need to build this adjacency list and this in degree map or array. So with all of this in mind, let's go with the code and hopefully you will get the idea. First, we have an edge case, which is if the number of nodes is 1, we return 1. Why? Well, because we know that the sum of values will always be divisible by k. So if we only have one node, we can return 1 right away. Now we need an adjacency list. This is a default dictionary with a default value of an empty array. That's why we use the word list. And we have an in degree map, which is a default dictionary with a default value of 0. That's why we use the word int. Remember that here you can use an array instead. So now we can iterate edges for a, b in edges, adjacency list at a dot append b, and adjacency list b dot append a. Now in degree a plus equal 1 and in degree b plus equal 1. This is exactly the same we did a few seconds ago. We need a queue for our BFS, and in Python we use a deck because we need to pop elements from left, and here we take every node. For node in range the amount of nodes, meaning n, if in degree of the current node is equal to 1. So now we have all the lifts in the queue, the result is initially 0, and we can start with the BFS. While we have something in the queue, every time we pop the first node, this is queue.popLeft, and every time we say in degree at the current node minus equal 1. Now we are checking if the value for the current node modulo k is equal to 0, we can add 1 to the result right away, meaning we have a new valid component. Else, we will add to our only next option, meaning to the only neighbor, the current value, meaning the value for the current node. So we can store this in some variable, we'll call this to add, and this is values node. And here we say to add is initially 0. So now we are ready to iterate every neighbor. For neighbor in adjacency node, if in degree neighbor is equal to 0, we can just continue, and else we need to subtract 1 from the corresponding neighbor, so in degree neighbor minus equal 1. and now values neighbor plus equal to add. Remember that if the current value modulo k is 0, to add stays at 0. Else to add has the value for the current node. And that's what we need to add to values at neighbor. Okay? And now we're checking if in degree of the neighbor is 1, we add this to the queue. And this will go on and on until we iterate every node. Finally, we return result. So now let's submit this and see if it works. As you can see, this works and it's efficient. Maybe you can make this more efficient with a different code, but in terms of time and space complexity, this is efficient. So this is it for this problem. If you found this useful, please drop a like, subscribe, and see you in the next one. Bye bye.